Me well?
Yes.
Okay, so I'm going to talk about some work we are doing together, and thanks very much to him and to Kathleen, Mario, and Jesus for asking me to discuss this. And this has to do with breakup models, and in particular some benchmarks we are doing, which I'm going to tell you in a moment. So the plan of the presentation is a bit complicated. I hope to be able to go through all this. So first, I would like to discuss breakup mechanism in general, because it's not just one way in which you can have breakup. There are various ways, but in particular, there are various ways in which the experiments are done and various observables that are measured. Then I will talk about the formalism, and I will talk about the quantum mechanical model that Jean uses, my semi-classical model, and an extreme classical model, which is the Icono. And we will concentrate on this case of so-called knockout of a neutron from oxygen 14, because this reaction gave rise to a lot of discussions. So when Jean started to work with me, he was interested in checking this, and I was also interested in checking with him. And then there are some technical details which have to do with the peripherality of the reaction, the implementations of the various ingredients and kinematics, and so on and so forth. What I wanted to say is that if you like to interrupt me, it's all right, because being a little bit technical, it could be too late for you to wait until the end. So let's see what it is breakup when, let's say, we measure it. So suppose there is a projectile with a weakly bound particle, or in general, a particle which for us will be always a neutron on the surface. So a valence particle. Interacting with the target, this particle can be emitted if the kinematical conditions are good enough. And then if what is measured, it's just the core intact. So if we are looking at an inclusive type of reaction, then in calculating this, we have to consider all possible interactions of the neutron, for example, the neutron, with the target. Now, we are in the continuum, so this neutron is going to be like a free neutron interacting with a nucleus, and obviously, you know that it can have, on one side, elastic scattering, and on the other side, inelastic scattering. And these two process in free particle scattering give rise to what is called elastic breakup and inelastic breakup. So this is just an intuition, but I will show that the formalism contains this. Another case is when there are coincidence reactions. In these experiments, let's say. In this case, for example, one has a 2-neutron halonucleus like beryllium-14, and after interacting with the target, the 2 neutrons are emitted, but one of the 2 neutrons is measured in coincidence with the core of origin. So this is a different type of experiment. It needs a different type of formalism, and of course, this would correspond only to the elastic part of what we have discussed here, because the neutron is in coincidence with the core. So obviously, it has not been absorbed by the target. There is finally a third mechanism for breakup, which is important when the target is very heavy and the projectile neutron is very weakly bound. In that case, there can be an effect of recoil of the core that gives rise to an effective force on the neutron, which is then emitted, because it continues by some sort of inertia. So how to discuss all this? Coulomb breakup, there will be a seminar next week, so I'm not going to discuss this. I will basically concentrate on this so-called transfer to the continuum, which is also called by some other people knockout. So here are some examples of type of reactions that have been measured, and seminars that have been already given during this series. And I will concentrate on this case here, which is a knockout of a neutron from very oxygen 14. So apart from the interesting thing of understanding the breakup mechanism and the reaction theories, of course, one has some structure interest, and most often these reactions are studied to check the shell model or to check the more recent ab initio models. This is for the nuclei which are away from the value of stability, and sometimes they are even unbound, like beryllium 13, lithium 10. In the old days, these reactions were studied with normal nuclei. And in those cases, people were interested in the real transfer to low-lying resonances of the target and of the effect of the single particle states in the continuum when the angular momentum was very high. Now, so suppose we are starting with a simple nucleus, halo, in which the neutron is far away from the core. When it interacts with the target, if we are looking at nuclear interactions, the nuclear potential will be effective only along a small part of the trajectory. Now, I'm talking in terms of classical trajectories here because we are thinking of reactions at high energy, well above the Coulomb barrier, and because we know that the core is measured intact in those reactions, we believe that they are peripheral. And this is one thing that with the benchmark we have checked. And of course, we have still to understand how important are the internal part of the wave function, both the bound state and finally the scattering state of the neutron with respect to the target. But it's important to remember that on this small piece of the trajectory in which the potential will be active, and so the breakup will really happen, any kind of trajectory can be approximated with a straight line. And this is what allows us to think in terms of semi-classical models. And then just a word about the way in which we fix our reference frame. We will have the velocity direction as the z-axis, the relative motion velocity along the z-axis, and then there will be an impact parameter for the core, one for the neutron, and the relative motion is described by a trajectory which depends on time, and it's this relative distance. So is it all right up to now? Can you hear me well?
Yes.
Okay, so let's go on. So first of all, I will tell you about gene model. Gene model is a very sophisticated implementation of something which in the 80s was implemented theoretically by Chimura, Aston, and Vincent in these papers. And in those days, I mean, in the 80s, let's say, there were a lot of discussions. Almost everybody working in direct reactions was trying to have a model for breakup. And they all were very complicated because also the reactions in those days didn't clarify. I mean, the experience didn't clarify well the situation. So there were all these papers, and then finally there was a paper by, in reality there were probably hundreds more, but these are the more clear ones. Hussein and McVoy had the idea of starting to use semi-classical approximations. And so this paper clarified a lot of the mechanism. So in the end, one wanted to have a model for inclusive breakup, which means the core is the only thing which is measured. See whether we can understand what happens among these various models. And of course, it's numerically difficult because in these fully quantum mechanical models, you have to take into account everything, all interactions and time depend. I mean, There is no question of discussing trajectory because it's just quantum mechanics. So there were 20 years in which almost nothing happened. And apart from semi-classical methods, Bauer was one, and Brink and myself were the others. So there are these two types of breakup: elastic breakup, I said before, and inelastic breakup, in which the neutron interacts a lot with the target. This is what Jean calculates, and it calculates through this expression, which is a kind of Fermi-Golden rule, sum rule. It's a bit complicated to explain in simple terms. But here you have the wave function, which takes into account the full three-body wave function. And then one wants to see what happens when the neutron has this strong interaction with the target. And so this is the imaginary part of the effective interaction. And the main equations that Jean uses are explained in these two papers. Jean, if it is not all right, please correct me.
It's okay.
Hello? Yeah, okay. So here is a bit more discussion, but just in case someone wants to know later on. So what happens instead in the semi-classical model? In the semi-classical model, we had started a long time before 88, because we were studying transfer to bound states. And there, starting from DWBA and applying semi-classical rules, which means instead of sum over partial waves, we transform to impact parameters, and the distorted waves were approximated by WKB wave functions, and there were almost 10 years of work of various people, not only myself. We came up to an expression like this, much simpler to interpret, in which on one side one has the degrees of freedom of the core. So this is the core target probability that the scattering is elastic. It's the modulus square of an S matrix, and what allows us to say that we can compare two reactions in which the core is measured intact. Any S modulus square of S matrix in high energy limits looks like this in terms of impact parameter or angular momentum. So it's a kind of step function, but it's not steep, it's sort of smoothed. And there is a point in which this S modulus square has the value 1/2. This in traditional heavy ion physics has been called strong absorption radius. And it is very well known that a good approximation is something like this, something like the sum of the radii of the two nuclei, but with a large parameter, because this has to be more or less the grazing situation. So it's a little bit larger than the grazing. Then there is the probability that the neutron is emitted. I'm going to tell you in a moment. Depending on how the initial wave function is calculated, one can have a parameter here, which is either the spectroscopic factor, if, for example, we use shell model wave functions, or the asymptotic normalization constant if one uses ab initio wave function. So the probability that the neutron is knocked out is calculated through a time-dependent amplitude. This is a bit tricky, but what I want to tell you is that the time dependence is important. We have it because we have the trajectory description of the relative motion. And this is the initial wave function, which is calculated in a moving reference frame, because of course, you know, the projectile is moving in this reference frame. So this is Fourier transformed. And in time-dependent theory, the wave functions have the radial part, but also some exponentials, which take into account initial and final binding energies. In this case, final energies in the continuum, so it's positive from 0 to infinity in principle. and the energy of relative motion. So by calculating this, in the way I will tell you in a moment, one obtains something which is very simple and nice to interpret, because one gets a sum over the neutron target partial waves. Here we have J, not L, because in general this theory contains the spin effect also. But we can see that there are explicitly two terms. One which is 1 minus the neutron target S matrix, then modulus square, and the other is 1 minus the modulus square of S matrix. Now, if we didn't have this extra F factor here, this, you know very well, is the formalism for the free particle cross-section. And this will be the elastic part of the cross-section, this will be the inelastic part of the cross-section. In knockout, there is an extra term, which is this F written here and blah, blah, blah. And this basically is the Fourier transform of the initial state wave function. And the Fourier transform comes from the fact that here there is a time dependence. And you see this time dependence, sorry. Okay, so how do we get this, how do we manage to get this simple analytical formula? It's because we have analytical forms for the initial and final wave function. They are anchor functions for the initial binding, bound state, and final continuum wave function for the final state. We can use these wave functions because one can show, it has been shown in all these papers, that this integral here, which is a three-dimensional integral, this matrix element, can be reduced to a surface integral. And on the surface, one can use the analytical forms of the wave function, and in particular the asymptotic form of the initial wave function. Having done this, one can still do another approximation, go to small neutron scattering angles, and then the sum over partial waves becomes an integral, this time on the valence particle impact parameter, while before we had the other integral on the core target impact parameter. And then finally, the probability of knockout becomes this expression here, which is what maybe many of you have seen already. It's the iconal form of the knockout formalism, in which one has explicitly the Fourier transform of the initial state wave function, and here the S matrix core target would be calculated with an iconal phase shift. Okay, so is it clear so far? Hello?
Yes, yes.
Is there anyone who wants to ask questions?
I think
no. No, okay. So let's carry on. So the case we want to study is this one. Is the knockout of a neutron from oxygen 14 on a beryllium target. This case was measured experimentally. I'm going to tell you all about it. And it was a kind of shock case because the experimental data are these red points. And it looked very different from anything else that had been seen before. This is a paper, I mean, the data and the theory were published in 2012. And already many knockout experiments had been published with different types of spectra. So here I would like to stress a few things. First of all, the incident energy was not that high. Typically, knockout is measured at 60 to 80 MeV per nucleon. Second, the separation energy of the neutron was very high. So by simple energy conservation, if you subtract 23 from this, you would see that in the average, each neutron in the continuum would have about 30 MeV, which is not very much. Anyway, so by doing calculation with my semi-classical model, the total I get is this sort of green curve. Yellow is the absorption, so this inelastic breakup we are comparing with gene. And gene is instead this blue one. So here we can see, so what is this spectrum? This is the cross-section with respect to the parallel momentum of the car. This is what is measured in the experiment. So if we have to compare the blue with the green, and we see that there is a kind of squeezing of this spectrum with respect to what I get. And this is what we are trying to understand. If I renormalize gene spectrum, it becomes something like that. But the total cross-section that we get is the same. I mean, the absorption, this one, because I can calculate also the elastic, gene at the moment doesn't calculate that. So we get the same total, and we get the same total because we use the same implementation of parameters, which I'm going to tell you in a moment. So you see this spectrum, it's reproduced here. It's very deformed. While traditionally in knockout, one has very nice sort of symmetrical, more or less Gaussian spectra. And they were very well described by the iconal. The iconal would be this dotted curve here. But you see, in this case, would not work at all, while in other cases would be comparable to the transfer to the continuum. And these are other cases in which some long tails were seen in the data and reproduced in the experiment. So one question is to understand these tails, both in the calculation, but also in the experiment. And they were seen also in old times when people measured, for example, alpha tritium or alpha helium-3 or neutron transfer to the continuum to lead, zirconium. You see, there were always these days. And when a partial wave description of the spectra was done, it was seen that it was usually very high angular momentum, which contributed to this state. This, for example, is a calculation from Wolfgang Bau and his collaborators in the 80s. So first of all, we wanted to check whether this peripherality idea was correct, because that is the basis of the semi-classical model, in which we factorize what the neutron does with respect to what the core does. And so we have calculated, both Jean in his method and myself in my method, the total cross-section for each core target partial wave. In my case, it is for each core target impact parameter, and you know that angular momentum and impact parameter are related to these relations. And you see, in both cases, we find this nice kind of smooth function. When Jean uses the coordinates of oxygen 14 with respect to beryllium 9, he gets exactly like me. So the total is the same. It's just that the width is somewhat, I mean, I get a little bit more on top and less on the tails, and Jean gets the other way around. But this shows that clearly the reaction is peripheral and concentrated on a certain angular momentum, which is the grazing. And this was already mentioned. Something like this one would expect in terms of Hussein and McVoy paper, in which they had this nice plot in which they were discussing the core target as matrix, the neutron target contribution. Then Jean can calculate for the core the angular distribution. I cannot do that. So it has been very useful because my is an integrated theory on the angles. So Jean has calculated this angular distribution for the core, and it's very nice to see that it's perfectly classical. For each angle, we have just one value. There are no peaks, no dips, so no diffraction effects, nothing. And this one can be seen also if one look at the spectra, the kind of spectrum I showed at the beginning, calculated for each impact parameter or for each angle. They all have the same shape. For example, if you look at different angles, they are just a different order of magnitudes, because of course the more you are far away from the grazing, the less breakup you get. And again, I renormalized the case in which the impact parameter was very small. I mean, the smaller in this calculation, this 140. And I could see that the shape is the same as what one gets at the largest impact parameter, just the tail is a bit longer. So this suggests that perhaps these tails, which are a bit mysterious, come from trajectories which correspond to impact parameters a little bit smaller than the grazing. And now for the people who are sort of familiar with classical mechanics, when you have a nuclear potential, if you have a trajectory which enters a little bit the potential, but still at the surface, this trajectory can be absorbed and then still can go outside at forward direction, but it will be reaccelerated because the nuclear potential is negative, it's absorptive. This is something very well known. So it could be that one has an excess of neutrons of high energy, because this tail would correspond to neutrons of high energy, when the trajectory is just a little bit below, but not much, of course, because it has to appear again, such that the core is measured intact. Because of this, we wanted to check the initial wave functions. So we calculated, Jean calculated in potentials of different radii. And of course, these wave functions would give rise to different absolute values for the spectra. You see, the wave function which has more internal part, a smaller radius, this red one, would have the smaller cross section. But again, when I renormalize and put everything together in the final spectrum, it seems that this wave function has a bit more tail. So it could be that the wave functions that correspond to a smaller initial potential somewhat get a longer tail. Although the total cross section in absolute value, you see this 4.9 would be the smallest compared to 9.3, that is what we have as our comparison value. And so now I go to the implementation. Again, is it everything clear so far? I don't know. Hello?
I think so. So
Yeah.
nobody ask question right now.
Okay, so I go to some details. I have 10 minutes left, is that correct?
Yes.
Yeah, okay. So one key point, in order to be able to describe these reactions, is, and in particular, the reactions like this one, in which the spectrum is so terribly, let's say, unusual and deformed, and with this peak here, is to understand what happens at the neutron with respect to the target. It's not trivial at all. So in order to understand that spectrum, I worked almost 1 year to obtain what can be defined the most, I mean, almost perfect neutron beryllium-9 optical potential. And this is a work I did with Bob Charity, and we ended up reproducing. So these are the data: neutron beryllium-9, total cross sections. Oh, sorry. Elastic and, my gosh, and reaction. We were able to reproduce separately the energy dependence of all these data. In the paper, we have also the angular distributions for the elastic scattering. And in this way, we managed to have two parameterizations for this optical potential. I have a parameterization which is fully, how do you say, phenomenological, while Bob does it with the distorted, with the dispersive optical model. And what was important here was that we were able to reproduce this peak due to these two resonances. This is log scale, this is normal scale. Because you see, this peak here is nothing but the result of that peak in the neutron-target interaction. This is due to kinematics. And so when you have a target like beryllium-9, and in which the neutron target, let's say, free particle cross-section goes like this, and then you multiply, more or less, multiply, by the Fourier transform of your initial wave function. If you are in a region of high incident energy, like 80 MeV per nucleus, you have something smooth for the Fourier transform of the wave function, and something flat for the neutron target cross-section. So you are going to measure and calculate a spectrum which is again symmetrical. But when you are at low energy, like this oxygen 14 case, you feel a lot the effect of these resonances and strong increase of neutron target cross-section. And so the original spectrum, which could be due just to the Fourier transform of the wave function, is transformed a lot. This is the reason why in that experiment one got that terrible deformation of the Fourier transform of the initial state. And now, this is something else, but I want to tell you just quickly what this is about. When you do transfer to the continuum, so far we have been looking at this knockout, okay? But one can look also more explicitly, doing exactly the same type of experiment, so sort of missing mass experiment. You measure the core, which has lost 1 neutron, to resonances in a target like beryllium-9 or beryllium, beryllium-9 with 1 neutron transfer or 2 neutron transfer. In this case, if you have the correct kinematical conditions, you can see the resonances in your target. And it was easy to apply my model and the optical model calculation to the case in which we had 1 neutron transfer. But when there was 2 neutrons transfer, so from oxygen 18, we were building up beryllium 11, and this was done in Catania by this group. It was more difficult because neutron beryllium 10 is an optical potential that I cannot construct, because beryllium 10, it's also a nucleus which is exotic, so there are no data. But fortunately, there is a ab initio model by Navratil, Quaglioni, Yupen, Calci, and other collaborators. In their model, they get explicitly the neutron beryllium 10 S matrix. So because I just need, in fact, the S matrix, in principle, I need the optical model because I have to calculate an S matrix. But if I have directly the S matrix, it's even better. So by using their ab initio S matrix, we were able to describe in detail all these resonances in beryllium 11, not only the very well-known resonances like the D5R, but also discover that perhaps there is a 9-half state here. So this is just to tell you that this semi-classical model is useful because it contains the S matrix that some structure models can give us direct. And then the other part which one needs to discuss is just to go back. Here, how accurate it has to be the calculation of the core target elastic scattering. So this S modulus square. Okay. So this has traditionally been done in eikonal models through a double folding, which is called often T-Rho method. So one obtains a core target optical potential with 2 densities and some neutron-neutron cross-section. At some stage, because we have this good neutron beryllium 9 target, and most of these experiments are done with beryllium 9 target, I thought it would be useful to construct another optical potential instead, which we would call single folding, in which we fold the optical potential neutron beryllium-9 with whichever projectile density we have or core density we have. This would diminish the uncertainties because we don't need to have a neutron-neutron cross-section. We don't need to have an explicit form of the target cross-section. And so we have looked at the differences if we do these two things. So once that one gets this new nucleus-nucleus S matrix, the easiest thing to do to check how good is this model is to calculate a reaction cross-section. So this is just a benchmark for this part of the calculation. By the way, in the previous calculations, both Gene and Dye have been used this kind of optical potential to calculate the core target scale. And so here are some data for reaction cross-sections for a number of nuclei, lithium, beryllium, calcium, on beryllium-9. And doing the double folding standard with many different densities, we will never be able to get the experimental points, which instead we managed to get with this single folding. And this was another case, lithium. And then with this student of mine, we have studied all possible cases in which the projectile has different mass. And we have seen that the single folding gives always larger cross sections than the double folding. And if you think in terms of the knockout, this would mean that with this method, one would in general calculate knockout cross sections smaller than one would get with the double folding. And then if we look again at this parameter that I mentioned at the beginning, the small RS that gives the strong absorption radius, we discovered that with this single folding, we in fact get almost in all cases for every mass number, something which is from 1.3 to 1.4 Fermi. And at the beginning, if you remember, I told you we were using 1.4. And instead with the double folding, one gets something which is not so stable with respect to the change of mass. Then I have here some kinematics, but maybe I will not talk about this unless people ask me. And this is very complicated. And finally, what happens when we calculate with Iconal. So I did long time ago a paper with George Birch. At the moment, I have not repeated this calculation for oxygen 14 because I know already what I'm going to get. Anyway, the Iconal is never exactly the same as an optical model calculation. And this we all know, I think. Even at 100 MeV, if you look at the two terms that we have for elastic breakup and inelastic breakup, you see here this will be the term which gives the elastic, and this is the inelastic. There are always differences. And we calculated also these probabilities that then enter in the final impact parameter integral. They are centered, all of them are centered again at the grazing. These were different incident energies. And by the way, this was beryllium 12. On beryllium 9 at 78 MeV per nucleus. Even at 100 MeV, one still could see a little bit difference between diffraction semi-classical and diffraction Iconal. But I think the main reason of this is that, you know, when you go from angular momentum to impact parameter, there is always a little bit of uncertainty because this relation, L equal B by K, is very good at very high impact parameters. And here perhaps we didn't have high enough. And this was the same, but with respect to the neutron impact parameter. So the calculation, this was the calculation with the full wave function. This was with the asymptotic wave function. It was just a check of whether there was any mistake being done using Henkel function, but apparently there was none. So just a word. Can I say a word on beryllium-13?
Yes, of course, you have time.
Yeah, okay, beryllium-13, this will be a kind of experiment, as I said at the beginning, in which we start from beryllium-14 or boron-14 or something else. Here are all possible experiments that have been done so far. But then, in all cases, what is measured is a coincidence, neutron beryllium-12, okay? So you see, various experiments, it doesn't matter what they are. I will tell you if you ask me later on. If you look, they all have similar pattern. There is a big bump here and another smaller bump here. So when we did these calculations with Guillaume Blanchon, Nicole Vimont, long time ago, we used a model which was not adjusted. Nicole Vimont had the air-on microscopic model for these two halon nuclei, in which we knew exactly which was her sequence of states, which were the energies, which were the widths of the resonances. The only thing which we used as a fitting parameter was the scattering length of a possible S-state iteration. So we got this when we compare to the data by Ike Simon and collaborators, GSI data at relativistic energy. No, sorry, this was their fitting. This was our calculation. Then this was something Guillaume did in comparison, this calculation, to data of Randisi and Nigel R. They started from boron 14. This was an experiment by Fukuda and, Kondo, Nakamura, and collaborations at RIKEN. In all cases, we reproduced this big first bump, and we said it was a P state. We said not because we had some kind of fitting, because we used this model. And there it was, the P state with this width. And this was at this state with this other width. And so, sorry, this second bump, we said a long time ago, could be at this state. Okay. And the S state doesn't show up very much because it has this small scattering length and because the P is too dominant. So again, this is for people interested. So I have finished. Sorry, I'm a bit late, but I hope I have been able more or less to show you that the quantum mechanical transfer to the continuum or knockout is very complicated, numerically challenging. Only Jean so far has been able to do that. And has the very great advantage that basically all observables can be calculated. Semi-classical can be used, my semi-classical, let's say, in many cases to discuss small energy, low energy resonances. It can use S matrices that come from other models. It seems to be accurate. I cannot calculate core angular distributions, for example, because the model, in order to be analytical, needs to integrate over the angles. The iconal cannot deal with resonances of any type, so forget about resonances. If you want to use the iconal, it's good for the knockout, but starting from around 80 MeV. Otherwise, one gets momentum distributions that do not correspond in shape to the experiment. And so, resume of what we have understood by doing this. The inclusive breakup is dominated by final state interaction with the target. And we have seen why it's so important to have a neutron target very good optical potential. When the incident energy is not that large, there is this strong interplay between what the neutron does with the target and what the initial momentum distribution is. So one can get deformation and things like that of the final spectrum. If the energy is very high enough, like when the diagonal is valid, then one can get from the from the measured momentum distribution, one can get the information on the valence particle state, because these shapes are different depending on the initial L of the valence particle. From the total value of the cross-section, the MSU people, for example, have obtained a huge systematics of spectroscopic factors. In the case in which one has coincidences, one sees that using invariant mass method type of experiments, the incident energy is not so important, but it's very important to be able to describe, to have a good description of the neutron core potential. Then in general, elastic scattering, I mean true elastic scattering without knockout, and reaction cross-sections are useful because they help us fixing this interaction between the core and the target. And with this, I have finished. In my life, I have had a lot of collaborators. Here they are in sort of historical order. And last but not least is Jean, that is the main author of the majority of things I have shown you here. Thank you.